The universe is a vast and mysterious place full of wonders that have fascinated humans for centuries. From the ancient astronomers who studied the stars to the modern scientists who peer into the depths of space with powerful telescopes, we have always sought to understand our place in the cosmos. Today we're going to explore one of the most advanced telescopes ever created, the James Webb Space Telescope, and how it sees so far into our universe. Infrared light is a type of electromagnetic radiation that has a longer wavelength than visible light. It's able to penetrate through dust and gas clouds that block visible light, allowing us to see through these obstacles and observe objects that are otherwise hidden. The four main instruments on the JWST are the near-infrared camera, the near-infrared spectrograph, the mid-infrared instrument, and the fine guidance sensor, near-infrared imager, and slitless spectrograph. Each of these instruments has a specific function, and they work together to capture, analyze, and transmit data back to Earth.
Eric, why don't you tell us a little bit about Webb, and then we'll have a chance to ask questions and discuss.
Okay, well, thanks, Laura, and I guess the delay worked out well because now we have some really exciting news to talk about here. One of the first things that I like to talk about when I talk about the James Webb Space Telescope is say, well, who the heck is James Webb? So this is the James Webb that we're talking about here, not the ex-senator from Virginia, but the man who was really the architect of the Apollo program, NASA's second administrator. But the reason it's important for us here as scientists is that he is the person that insisted science be done within NASA. Many of you may remember that the Apollo program was really showing American superiority to the Soviet Union. We're going to beat them to the moon. We have the best rockets, all that. That's really all that Kennedy cared about. But Webb, who was a bureaucrat by training, knew how to work the levers of government, knew that he had to have the best scientists and engineers to complete what the president wanted. And to get those people, he had to let them do their science and engineering research. So the only reason we have science at NASA is because of James Webb, who was a lawyer by training, actually.
By studying the earliest galaxies, we can learn more about the formation and evolution of the universe. We can also gain insights into how galaxies like our own Milky Way formed and evolved over time. The Hubble Space Telescope has revolutionized our understanding of the universe, and the James Webb Space Telescope is poised to take us even further. With its advanced infrared capabilities, the JWST will allow us to see deeper into space and study the earliest moments of the universe. It's an exciting time for space exploration that we can't wait to see what discoveries the JWST will bring. Certainly, here are some additional interesting facts about the James Webb Space Telescope. The JWST is named after James E. Webb, a former NASA administrator who played a key role in the Apollo program. The telescope is a joint project between NASA, the European Space Agency, and the Canadian Space Agency. The JWST will be positioned at a location called the Second Language Point, or L2, which is located about 1.5 million kilometers from Earth. This location allows the telescope to have a clear view of the sky and avoids interference from Earth's atmosphere and heat.
We needed to test the telescope and the instruments together. So first a little bit about how that telescope works. We're called a three-mirror anastigmat design. So we have three main mirrors, elliptical, a hyperbolic, and another elliptical tertiary mirror. But there's also a flat steering mirror at the end that we can use so we don't have to slew the telescope for small motions. We can just move that mirror a little bit. The mirrors, as I may have mentioned, were made of beryllium. Each mirror segment can be controlled in piston, tip, and tilt, and we can also adjust its radius of curvature. So even though they look flat to the eye, there is some optical power in them, and you can sort of push the center in and out. We know that when we launch this, it will be out of focus. Just giving you that warning right now. But we can adjust it. In fact, because it's this infrared telescope that has to work at extremely cold temperatures, the mirrors now, they're out of focus because they're at room temperature, and it only comes into focus when it's extremely cold. It's part of the reason why it takes us so long from when we launch to when we get data back. We have to cool down so that the mirrors are smooth as they were supposed to be at cold and not bumpy as they are at room temperature.
JWST's primary mirror is made up of 18 hexagonal segments that will be assembled in space after launch. Each segment is about 1.32 meters in diameter and is coated with a thin layer of gold to improve its reflectivity. The JWST has a sun shield that is both about the size of a tennis court. The shield is designed to keep the telescope cool and protect it from the heat of the sun and Earth. The JWST is expected to operate for at least 10 years, and its mission will include studying exoplanets, star formation, and the evolution of galaxies. The cost of the JWST's development and launch is estimated to be around $9.7 billion. Overall, the James Webb Space Telescope represents a major leap forward in our ability to explore the universe and unlock its secrets. We can't wait to see what discoveries it will make.
So this is an animation that folks at Northrop Grumman put together showing the sequence of events. Once we get released by the upper stage from the Ariane, we go through a series of maneuvers and deployments. You can see on the top the time after launch, the distance will come up with the activity, and you can see a little graph showing where we are in our journey. The solar array comes out very quickly, so we have power. We start to do any course corrections we need to make sure we're going to the right orbit out there at L2. The smaller the correction we have to make, the longer our life is because it saves fuel. Right about the time we get close to the moon, our high gain antenna comes out so we can communicate at a high data rate. You can see about 2 days we're past the moon. Now we begin the major deployments where what's called a pallet that holds the sun shield, the forward part folds down. We'll follow that by folding the back part down. I got to watch them test this at Northrop Grumman. They do a gravity offload to test the system. Now once those are down, we want to move the telescope away from the spacecraft because it is a little warm itself, so we telescope up on a tower about 5 feet. Now the covers that protected the sun shield during launch are released and they roll back. Some covers in near the spacecraft core do the same thing. And once those are released, we can actually begin to push out concentric tube telescope booms to extend the sun shield. There are 5 layers to this sun shield, and it's critical that there be separation in these layers so that heat from one layer can escape out before it hits the next. So they'll tension up the system, which is just a pulley system that raises the layers apart and provides tension to them.
Thank you for watching. If you enjoyed this video, please like and subscribe for more science content. And don't forget to keep looking up.